Hello friends, welcome to part 2 of the regularization. In the first part, we learned about L1, L2 regularization. We understood about the bias variance trade-off. We understood about the need for regularization, which is to overcome overfitting. All these things we have seen. Let's try to see more details now about L1 and L2 in this particular video. Let's start. So we have already discussed this particular thing, that common regularizers are L1. This is the L1 regularizer. This is the L2 regularizer, right? The primary difference between L1 and L2 is that we are taking the L1 norm, right? Which is beta j, the absolute beta j. In L2 norm, we are taking the square of it, right? This is the primary difference, okay? Now we have also dealt with about the norms, right? We know that this is the way first norm is denoted, right? L1 norm is denoted by pipe and 1, and the expansion of that will be x1 plus x2 plus xn, right? The second norm, or L2 norm, is nothing but x1 x square to xn x square under root, right? In a more generalized form, in p norm, we know that xp, x1 to the power p summation, and then we have to take a pth root of that, right? So this is the p norm, right? So over here, if I have to go, right, again, just to recap, we know that the L1 norm is also called as Manhattan distance, right? Why? Because the distance over here, and this has already been discussed in the previous video, the distance is beta 1 plus beta 2, right? If I have to arrive at this point, which is beta 1, beta 2, I will go here and here. So this distance beta 1 is this distance. Let me write it in a different line. So this distance is beta 1, this distance is beta 2, right? So my beta 1, beta 2 is a distance, covering distance like that. If I cover the distance in a more straight line, right, joining these 2 points, that is Euclidean distance, right? We already must have learned this in our coordinate geometries and all in high school. That is nothing but our beta naught 0 whole square plus beta 2 minus 0. 0 is the center or the origin, whole square under root, right? This term is represented as Euclidean, and this is L2 norm, right? This distance. More generalized form, the p norm will be beta 1 till beta 2 the whole to the power p under root. So beta 1 to the power p plus beta 2 to the power p plus and beta n to the power p, and this whole underscore under root pth root, right? That will be p norm, right? And in a multi-dimensional space, this pth norm. But for our current use case or current learning, will mostly be concentrating on L1 and L2. So the difference, the primary difference, again to repeat L1 and L2, is this is my L1 distance, right? Absolute distance. L2 distance is the square distance, right? So this is L1 distance, this is L2 distance. Just remember that, okay? And the notation, as I was seeing, L1 is notated like this, 2 bars, within 2 bars, and if 1 is written subscript, that means L1. L2, 2 will be written. On the pth norm in a more generalized, p will be written, right? So this is what L1, L2 norms are, okay? Now, how do we visualize our p norm, okay, pth norm? So this is an interesting thing, and let me go to GeoGebra and show you over there how it works, okay? Okay, let me open this. Okay, yeah, this I have already drawn, but I would like to show you, so let me just remove this. Okay. This is the x square plus y square is equal to 1. GeoGebra is a fantastic tool to draw equations, right? So I'm trying to draw a x square plus y square is equal to 1, right? This is the equation of a circle with radius 1. Everybody knows, right? This is how the circle will look like, with center as a origin, right? 0, 0. Okay. Now, this particular thing, if you know, when I'm writing x square plus y square, you think that this is beta 1 and beta 2. So beta 1 square plus beta 2 square is equal to some value, will be represented by a circle. If I increase the order, right? If I increase the order, now it will be beta 1 to the power 4, beta 2 to the power 4 is equal to 16. If I draw something like that, you see it from circle, it has gone, as we increase the power or the norm, it has gone and approached a more squarish shape, right? Squarish shape. Do you appreciate that? Yeah, this is approaching a more squarish shape. If now the third thing, this is the green line, it's beta 1 4 and beta 2 4 to the power 4. If suppose I have to draw now the third thing, right, the absolute, the L1 norm, if I have to draw, what was the formula of L1 norm? Modulus x1 modulus x2 to modulus x3. In our case it will be modulus absolute beta 1 plus absolute beta 2. I keep saying modulus, but absolute beta 1 absolute beta 2. Okay, so equation will be absolute x absolute y. This is beta 1 beta 2. Let me show how it looks like. The equation of absolute beta 1 absolute beta 2 looks like this. It looks like a square which is rotated by maybe 45 degree, right? It's a square which is rotated by 45 degree. Now, why I am showing you this? Okay, so as when we increase the norm from p is equal to 1 to p is equal to 1.5 to the power 2, 2 becomes circle, right? P1 was a square by 45 degree. P2, when the L2 norm came, it became a square. We saw that, correct? We saw that L2 become a square. When we went to 4, it started approaching a more squarish shape. When P approaches infinity, it will be a perfect square. This is how the figure looks like geometrically. Okay? Now remember this. Now the question is that why it is important? Why I was showing you this this norm thing? The reason why I'm showing this will become evident in just a while. Just hang on. Okay. The thing which I'm trying to say, initially, if you notice, I just told you that this is my loss, right? Which I was trying to minimize. In a standard cases, this is my MSE loss or RMS loss, and I will try to minimize. Then I'm adding a beta term, right? In a L1 penalty or L2 penalty, I'm adding it like this, right? This same thing can be represented slightly differently in a mathematical form. How? We can formulate our equation in such a way that, hey, minimize my loss such that, or subject to, I do not want my betas to grow beyond a point. I do not want my sum of absolute betas to grow beyond a point in case of L1 penalty. Similarly, minimize my loss such that, and this is an extra condition which I am trying to add, right? This is effectively saying the same thing what we have seen in the formulas earlier. Minimize my RMS or MSC in such a way, conditional to or subject to, that my L2 penalty or beta j square should not increase beyond a point, right? Should be constrained. This is putting a constraint, right? This extra condition is putting a constraint, right? It is saying the same thing, correct? Now let's see that how that works. Okay. Now, if you notice over here, forget about these circles for now. If you notice about there, then beta 1, beta 2, I showed you in the GeoGebra, right? My L1 penalty region will look like this, right? It will be a square tilted 45 degree, correct? My L2 penalty will look like a circle. For now, just try to this green area, right? What is this shaded area? This shaded area is nothing but this particular equation. What is this equation saying? That my beta j should be less than a particular number, right? Some constant. Over there in GeoGebra, what I was doing? Absolute x, absolute beta 1, absolute beta 2 should be equal to 1, right? If I do less than 1, what it will mean? Less than 1 means all the regions inside this, right? Less than equal to 1 means all the region which is inside this square, right? This is what being represented, the shaded green region. And this is what is being represented by this particular conditions, these two conditions. This is the condition which is saying that, okay, all the points which is within that circle will satisfy this condition. All the points which is within that square will satisfy this condition, correct? Just remember that. For now, don't worry about this. I will just explain in a bit, okay? Let me go over here to explain further, right? Now, what was our initial loss, right? Let's see, I'm taking the case of beta 0, beta 1, beta 2, only 3, simplified case. My MSE or RMS will be yi minus beta 0, beta 1 xi plus beta 2 xi the whole square, correct? What will be if I include the L1 or L2 penalty? Let me see that if I am including L2 penalty, what will be my MSE? MSE plus lambda beta 1 square plus beta 2 square, right? Now, when we are seeing that particular condition, can we rewrite it in a different form? We can rewrite that our equation can be rewritten in different form, which we are saying that minimize my MSE subject to this particular condition. This was a constant anyway, so I am putting constant c square just to say that this c represents as the radius, right? This c will become the radius of this circle, right, which is represented by beta 1 beta 2, right? The c will become circle, so I am putting c square over here subject to c square. And what is this particular condition? This particular condition is represented by all the points within this circle of radius c, right? Correct? This is the geometrical interpretation of this. What the Lagrange multiplier, and this is a way in which lot of optimization problems, convex optimization problems are solved, right? The details you can look up on the internet, but I'm trying to give you a flavor of it, that how these two conditions, that this minima subject to this is being solved, right? It is being solved through Lagrange multiplier. What it will do, my loss combined will be what? RMS subject to this particular condition less than or equal to 0. I have just brought it on the other side, right? Less than equal to 0. This is the condition. Similarly, my loss now this combined loss will be a function of beta naught, beta 1, beta 2 and lambda, right? And we have to minimize this loss. Whatever is the minimum of that loss and whatever beta naught, beta 1, beta 2, lambda arrive, that is my model coefficients, correct? So RMS, I can write it as plus lambda this thing, right? To solve this particular thing, what we need to take the gradient of this, right? Of the gradient of this loss function. So taking the gradient of this loss function, we have to take the partial derivative of this particular thing. And the partial derivative of this particular thing, which is a function of this, will be del L by del beta naught, del L by del beta 1, del L by del beta 2, del L by del lambda, right? All four variables will come inside. And when we equate to 0, right? Now, one other thing is to notice that lambda and c square, both are constants, right? So this particular thing will become a constant. It will not have any impact on my minimization problem, right? So we can ignore that, and it becomes that's why c is not coming over here. If somebody, one of you is raising that question, that c is not coming because it's a constant, right? So this is my del L, and this becomes my minimization problem, okay, through Lagrange multiplier. And when we solve that, this is the way actually it is solved, right? But we are going to use the open source packages and all, but typically this is solved using Lagrange multipliers, right? Now let's try to understand the difference between L1 and L2 loss, right? So friends, we have already discussed that what is this tilted square, tilted by 45-degree square, and what is this circle. These things are nothing but these L1 penalty and L2 penalty, right? Which we are writing, and which goes into Lagrange multiplier also. This is nothing but that. And how we know? We have shown it through GeoGebra that the equation of beta, absolute beta 1, absolute beta 2 is equal to some constant will be equal to this rotated square, right? And beta 1 square plus beta 2 square is equal to some constant will always be a circle, right? And as we increase the p norm, it approaches a squarish shape. We already know that. So friends, we already know that in beta 1, beta 2, and this is our model coefficients, beta 1, beta 2. What is this green shape, right? Circle and square is, right? Now let's try to understand what are these ellipses. Okay, these ellipses are nothing but my first condition, which is the original loss, MSE or RMS loss. So this particular loss, MSE or RMS loss, is being represented by those ellipses. Let's try to see how these are represented. So this, let's say, in absence of any penalty, this was my, this beta, this particular point was my global minima, right? MSE loss is a convex function. It will have a minima. Let's say that was the minima. Okay. Now what this equation is telling us, this equation is putting a constraint over here, constraint in such a way that this equation and this equation should be true at the same time. should satisfy at the same time. This should also minimize and this condition should also satisfy. How it is going to happen? These ellipses are contour maps of our mean square errors. Let me repeat that. This one inner circle, if you see, this is for a particular value of RMS or MSC. This particular MSC, right? This particular MSC, this line which you are seeing is a fixed MSC, right? So here MSC, let's say, was 2, for example. 2 was the minimum which would arrive, and my SGD or gradient descent arrive at 2, right? And our beta naught or beta 1, beta 2 parameters were 5, 5, okay? If I have to satisfy this particular condition also, then I have to expand, I have to increase my error. When I increase my error, this is the ellipse which I make. So this, let's say my MSC increased to 10 now, okay? This is ellipse. Increase to 20, this bigger ellipse. Increase to 30, this bigger ellipse. Why I have to increase the ellipse and my error? Why I have to do that? I have to do that because simultaneously I have to satisfy this condition also. Wherever these increasing ellipses touch the first point of this diamond or square, will be the beta 1 and beta 2 which we are interested in, right? Because why? Whenever the first ellipse, we will slightly keep expanding the ellipses. Keep expanding the ellipses, that we are increasing the MSC bit by bit, right? We are increasing the MSC in such a way that I should satisfy the other conditions also. The other condition is the blue condition, right? The green condition over here. So I'll try to expand my MSC. The first point where this MSC, which is represented by this contour map of this ellipses, and the last ellipse, right, which you are seeing, probably is touching over here. Correct this? So this particular point, wherever this ellipse, an ellipse represents a constant MSC, wherever this ellipse touches my constraint, which is L1 constraint, and their meeting point will be my ideal beta 1 and beta naught, beta 2. Why? Because at that point my constraint is also meeting, as well as that will be my minimum beta, my minimum loss which I can afford for satisfying the constraint. Correct? That particular meeting point is this. Similarly, in case of lasso also, this will be a circle. This is the same thing, my original loss, mean square loss, and I'll keep expanding, and wherever it meets, I will try to do that. That meeting point, wherever it is meeting, that meeting point will be my ideal beta 1 and beta 2 model coefficients, right? So what is the difference between L1 and L2, right? We'll just see. One thing which we always say, and the people say, that L1 is better for feature selection also. It is not just for regularization, but it is also used for feature selection. Let's try to understand what we mean by that. And this can be best explained graphically like this. Now friends, try to pay attention here. Now when these ellipses are increasing in a two-dimensional end space, in two feature space, beta 1 and beta 2, what are this particular shape of lasso of ridge is a circular shape, right? This particular shape is a squarish shape. In a 2-dimension, it is represented as a square. In a 3-dimension, it will probably be a cube, tetrahedron. Now imagine this in a multi-dimensional space. In 2-dimensional, it is a circle. In 3-dimensional, what it will become? It will become a sphere. In multi-dimensional, it will become a hypersphere. Probably our human minds can't gather that. But one thing is for sure, right? And intuitively you can understand that why it is used for feature selection is the reason that whenever we are expanding these ellipses, there are far greater chances that because of this inherent nature of the shape of L1, these ellipses will meet when on the axis itself. The meeting point will lie on the axis. And what does it mean if the meeting point lie on the axis? That means, what does it mean? That means the other betas become 0. Some of the betas will become 0. In this particular case, if it is meeting at here, that means my beta 1, my beta 2 has some value, 4, 5, whatever is the number. But my beta 1 is become 0, right? So it will be 0.05, right? It is meeting at 0.5. My beta 1 has shrunk down to 0. What does it mean? That means I am no longer paying attention to the feature which is attached to my beta 1, and only I will pay attention to beta 2, because beta 2 is the feature which is doing most of the explanation, or which is able to explain most of the variability associated with my data. Okay, this is what it means. And that's why in case of L1 it is also used as a feature selection. If somebody asks you that why L1 is used as a feature selection, Lasso is used as a feature selection also, this is the answer for that. Let me repeat that. In case of 2 dimension, it is very easy to assume that the ellipses which will keep growing, there are far more chances that it will meet on the edge, right? It will meet on the axes, right? Because of the inherent shape of this. In case of this circle, in case of ridge regression, because it's a circular shape and not a tilted shape, right? The chances are that it will meet somewhere else over here. So my beta 1, beta 2, and this meeting point is also my ideal point. That's the point when my constraints are satisfied and my loss is minimum. Both the conditions are done. The chances in Lasso to meet that on axes are far smaller. That's why none of my model coefficient parameters will go down to 0. Okay, it will reduce, but it will never become 0. Correct? This is the intuitive and geometric answer for why Lasso is better for feature selection. If you have any question, this is very important. If you have any questions, please put it in the comment and I'll try to answer all your questions in a better way also, right? But just to repeat, the shape of Lasso is like that. The constraint of the Lasso, which we are seeing, this constraint is like this. The other mean square error is the contours, and the contour is nothing but my mean square error, the separate MSC. This is MSC 5, this is MSC 2, this is MSC 1, something like that, right? Where I keep expanding my MSC so that I'll satisfy this condition also. When I'm satisfying, in case of Lasso, because of its shape and in a hyperdimension space, there are more chances that this will hit on the edge, on the axis itself. And when it hits on the axis, that particular corresponding beta will have value, but the other betas, there will be lot betas which will go down. In this particular case, beta 1 will shrink to 0. If beta 1 shrinks to 0, that means we are ignoring that feature itself. How? If that coefficient itself you are putting at 0, that means you are ignoring that. In the equation there is nothing. 0 into xi, 0 into x1, right? It will become 0, right? But in case of ridge regression, that is not happening. It will try to minimize those beta 1 and beta 2, but it will remain, there are very small chance that it will hit at the corner or the edge and it will become 0, right? That's why Lasso is used for feature selection. Now, before I close, there are a few other points to remember. Regularization should only be used during training. At time of test prediction, use unregulated model. Now, why? Why is that? So this is a very important point. Don't put your regularization on both training and test. What we are trying to do, we are trying to achieve at a more regular, low variance model, right? A better model. Once the model is arrived, you have to fit or you have to do the prediction on the original model, right? On my original line, y is equal to mx plus c. Again, you do not have to put the penalty over there. Okay? Always scale the date before using, no, this is not date, sorry, this is data. Always scale the data before using regularization. Why data should be scaled? And this is very important. Whenever you use regularization, always use a standard scaler, min-max scaler or something to bring the point, right? And the answer over here also lies over here. Let's say if you do not scale the data and my beta 1 or this parameter is on a completely separate scale. On my x, the first feature is on a completely separate scale, second feature is on a completely separate scale. Now what will happen? If you recall the equation, right? When we are trying to minimize with the L2 penalty, then lambda beta square is there, and in the main loss there is also a parameter which is xi beta a square, right? X square beta square in the main loss itself. That x square will have an impact on how my optimizer overall reduces the values of beta. Let's say if your one feature is at a very different scale than the other feature, the optimizer will not be able to do a good job in reducing those betas. But in the situation where you have done a standard scalar, min-max scalar, normalization, you have already done that, then these x's all are in the same range, right? Then your beta will be reduced accordingly, right? In a nice way. So that's why it is always preferred that you should do your standardization, normalization before you use regularization. Now, this I have already told the third point, that beta naught, right? The initial intercept term, we do not put penalty for that, right? And if my lambda becomes very, very high, what will happen? Okay, we'll say cross validation is used to arrive at the lambda. There is no fixed value of lambda which you should take, right? The lambda can range from 0 to infinity. What will happen if lambda is 0? It's just a standard loss, right? So whether it's a logistic loss or your standard linear regression, MSE loss, whatever that loss is, ordinary least square, right? OLS, whatever that loss is, that loss will remain. There is no penalty term which is added. But if lambda is infinity, what will happen? Then y will approach beta naught. Why it will approach beta naught? Because every other term except for beta naught, because beta naught we have not put a penalty, every other term will become or tend towards 0 because lambda is so high. Optimizer will see that lambda is so high, the only way I can compensate is I can bring down all the coefficients to 0, right? That's the only way it can compensate. And what will remain? The remaining term will be beta naught. So for every prediction you will get beta naught, right? Let's jump on to Jupyter Notebook and see how with the scikit-learn we can make it work. Okay, so this is my regularization Jupyter Notebook. I will try to go it through. And what we are doing is we are importing scikit-learn packages. So scikit-learn has API for Ridge, Lasso, and ElasticNet. ElasticNet is nothing but a combination of Ridge and Lasso. That's what. So as long as you understood L1 and L2, you should be good. Okay. We are importing bunch of packages, and we have imported our Boston housing data set from somewhere on the GitHub. I found it and I downloaded it. Okay. I do the df head, df info, all those things are correct. Okay. And what I do is I will do a train test split. Nothing great over there, standard things, train head. I do the head, it shapes 354 data in training, 152 in test. Okay, nothing. Now this is our, what I'm trying to fit over here. What I'm trying to do over here is, my standard linear regression model, right? So it's train, Y train, and without all the default parameters, I will try to fit it. Okay, let me fit it. What did I get? My training error is 74%. Training score is 74%. MSE is 4.63. Test is 71%. Not too bad. They are very close. So it's good, right? Standard linear regression gave me this prediction. Now what I will do is I will try to make it overfit. This data is linear, right? I will try to put a polynomial feature of degree 2. That means I'm expanding the features, right? And this is how I'll expand the feature. Okay, I expanded the feature, and then my new X train and X test becomes expanded, right? Now they have multiple second order features also. Okay, now if I run my vanilla linear regression on this expanded polynomial features, right? Let's see what happens. Similarly, I went from 74% over here, I reached to 90% over here. Why did it happen, friends? Because again, if you recall our initial discussions, right, then I'm making a more complex model, right? So what will happen? I will land in a high variance situation because I'm adding more polynomial orders over here, right? I'm creating new features with polynomial orders, and the data is fitting more and more closely to the training data. Okay, what happened to my test score? The test score in case of linear regression was 71 with the original data sets. When I did a overfitting, it reduced to 59%. If anywhere you see my training score is 90%, my test score is 59%, this is a classic case of overfitting, right? Now let's see. Now my data has polynomial orders also. Let's put the ridge regression on this, right? Ridge regression, L2 penalty. So the way to call L2 penalty is like through ridge, right? We imported this API. We'll call max iteration. I'm setting to 10,000. Alpha is nothing but lambda. It is called in scikit-learn alpha, so you can ignore that. Okay. What I will do is I will try to start with maybe 10 alpha. Okay. I'll try to see what is it. 93% training and test has increased from 59 to 73%. That means I'm reducing the variance, right? By reducing the variance, my test score is also increasing now, right? I'm reducing the variance, increasing bias little bit. My test score is improving. So I'm going into the, if you recall the figure, right? Let me show. Yeah. So from this region, I'm trying to do this towards this region, right? When I'm going towards this region, what is happening? My test error is coming down. My test error is coming down. It has still not reached the sweet spot, but my test error is coming down. And what will happen to my training error? My training error will start climbing down because I'm reducing variance, right? Okay. So it has gone from 90% to 93%, right? Okay, it has increased actually, but my test error has gone way up, right? So let's try to increase the lambda further. Okay, if I increase lambda, it's become 92%. My test error further increased, so I'm reducing the variance, right? It is putting a penalty. I increase 1,000, it is 90%. So initially it was 90%, now also it is 90%. Let me put 10,000 as lambda. What happened? My training error is 89%, but my test error has increased to 82%. From 59%, my test error has increased to 82%. This is the region where I am, because of my L2 regularization, I am going downhill and I'm reaching the sweet spot, right? Again, the value of lambda or alpha can only be done through cross validation. I'm just showing you an exercise that how it impacts, right? Similarly, if you do with the L1 penalty, it's the same thing, right? We'll start with 10 maybe. Okay, so L1 penalty gave me 86% training and test as 80%. If I increase 100, okay, so this is going in the area where it is increasing the bias. Like maybe for L1 penalty, this lambda 100 is too much, right? If you see, my test score is not increasing, it has decreased. My training score has also decreased. What does it mean? That means I'm going in the area of this area. I'm climbing uphill now, right? I'm going in the area of high biasness, right? So I probably 100 is a way over penalty, and it should be like, let's say if I do 50 over here, right? This is the spot, 83% and 80%. So you have to do cross validation and do that. Okay. Now I was saying that elastic is nothing but L1, L2 penalty combined. This is the formula. This is the L1 penalty, L1 non, L2 square. What is elastic? Elastic is a combination of this, and how much is the weight of L2 or L1 is defined by this parameter, right? There is a, so they both are there, but they are both present in a weighted, like in a proportion. What that proportion is defined over here. So you again you put the how much penalty you want to put, but what is the L1 ratio of this? So if I set L1 ratio as 0.5, that means half L1 penalty, half L2 penalty. Okay. If I set the L1 ratio as 0, that means full L2 penalty. If I set L1 ratio as 1, that means full L1 penalty. No, it will just behave as a L1 penalty, right? Okay. Similarly, you can do it over here. This is just elastic regularization, right? With that being said, I think we have come to an end of this, and I'll see you all in the next video. Till then, bye.